Alright, let's go over the second example of how to balance redox reactions by the half-redox method. We have permanganate reacting with elemental tin, forming manganese 2 plus and tin 4 plus. Alright, so we're gonna once again balance this equation by the half-redox method. And by the way, if you're unsure as to whether this is a redox reaction or not, all you have to do is look at, and if you can, look for the simplest case scenario, right? If you look at tin, where the charges are basically given to you, the charge of the first tin is 0, and the charge of the tin on the product side is 4 plus. The fact that the charge is changed is telling you this is a redox reaction. So you might want to balance it by the redox method. All right, so here we go. We're going to break this up into two halves, the manganese half and the tin half, right? So that's the first step in the half redox method. Then what we're going to do is we're going to balance all the non-oxygen, non-hydrogen atoms. That means manganese and tin in this particular example. We have one manganese on both sides and we have one tin on both sides. So they're basically balanced. So we need to do nothing there. That's basically done for. So we move on to the next part, which is to balance the oxygens. And we do that by adding enough waters to whichever side is lacking in oxygen. So looking at the left side of the first equation, we have 4 oxygens present. The product side has no oxygens. So that means that we're missing a total of 4 oxygens on the product side. We make up that discrepancy by adding 4 waters. For the second reaction, neither product nor reactant has oxygen, so there's nothing that needs to be done there. That's basically balanced from the point of view of oxygen. Now we need to balance the hydrogens by adding enough H pluses to whichever side needs it. And on the first equation, we have 8 hydrogens on the right side. We have no hydrogens on the left side. So we'll add 8 H pluses to that particular section of the equation. Once again, the second equation doesn't have any oxygens, doesn't have any hydrogen, so we don't need to do anything in terms of balancing oxygen or hydrogen for the second equation. All right, so now we start looking at the electrons, and here's where the charges, the overall charges come in. So in the case of the first equation, we have 1 permanganate with a charge of -1. We have 8 H pluses with a +1 charge. So we have -1 plus 8 being equal to 7. And on the product side, we have only 1 manganese with a 2 plus charge. Water doesn't have any charge, so you end up with an overall charge of +2. Here on the bottom for tin, the charge is just 0, so that's the overall charge of the reactant side. And for the product side of tin, you have 1 tin with a 4 plus charge, so the overall charge is 4 plus. So once again, we look at the discrepancy, right? We look at the change between the charges. So 7 minus 2, that's the difference between the two overall charges, is 5 electrons that you're missing. 0 minus 4, absolute value, is 4 electrons, meaning that you are missing 4 electrons altogether. So you just want to place those corresponding electrons on the side with the highest charge, which for the first equation, between 7 and 2, 7 is the higher charge. Between 0 and 4, the higher charge is 4. So that's where you want to place those electrons. 5 electrons on the left side, 4 electrons on the product side. And like I said in the previous example, by the time you get to this point, you should have electrons on one side of the first equation, and you should have electrons on the opposite side of the second equation. All right, now we need to balance the number of electrons. And cross multiply may be all you need to do. If we look at the number of electrons, 5 and 4, there is no common denominator for them. So you will literally just cross multiply the equations by them. So the first equation gets multiplied by 4. The second equation gets multiplied by 5. So distribute the 4 throughout. You're going to have 4 permanganates plus 32 H pluses plus 20 electrons, yielding 4 manganese 2 pluses and 16 waters. And for the second equation, we'll have 5 tins, yielding 5 tin 4 pluses and 20 electrons. All right, so now that everything is balanced, including the electrons, now we add them together. And when you do that, the electrons are going to cancel out. If you do have waters on both sides of the equations and H pluses on both sides of the equations, make sure to cancel them out to the highest extent possible. But in this particular instance, there's only H plus on the left side of the first equation, and there's only water on the right side of the first equation. So you will literally just bring everything down the way it is, because there's nothing to be canceled out aside from the electrons. And once again, everything that's on the left side of the equations needs to remain on the left side when you bring them together. Everything on the right side of the equation needs to remain on the right side when you bring them together. All right, so that's the second example. Now, we've already talked about the activity series in the past, but I want to refresh your memory because it kind of plays a role here, being that we're dealing with redox reactions. So this is more a refresher than anything else, but this is the last part of the lecture that I need to talk to you about. All right, so we know that we have a lot of metals in the periodic table, right? We have 11 elements that at room temperature happen to be gases, right? The ones that I'm highlighting in blue here are gases. You have 2 that are liquids at room temperature, and this is elemental, by the way. So bromine elemental is a liquid, mercury elemental is a liquid. Everything else, however, is a solid, right? And you have a lot of solids which are metals as well. So there's quite a bit of substances, but this is something you have to keep in mind because when dealing with the activity series, we are going to have elements that are present by themselves in their elemental form. And so you have to remember what is a gas, what is a liquid, what is a solid. Pretty much, if you don't have one of the elements that is a gas or a liquid, it's automatically going to be a solid, even if you haven't really played with the thing in the past. Like if I give you hafnium, even though this may be the first time you see it, because it's neither of the Hofbrinkel elements or noble gases, it will not be a gas. And because it's not bromine or mercury, it will not be a liquid. So by process of elimination, this had to be just a solid. All right, so as you may remember, the activity series is a list of how well the elements can undergo, oxidation or reduction. And at the time, I didn't really refer to them completely that way. I just told you, where they lie and how you place them. But the idea is that the higher up on the table you are, the more reactive you are as a species. And we're talking from the point of view of the reactant. And so if you were to combine any of these elements with another one, you can assess whether a reaction is going to happen or not just by looking at the activity series table shown here on the left side. So to give you an example, you could be combining aluminum metal by itself with iron 2 nitrate. And what you would need to do is focus on the aluminum. You'll have to say, all right, aluminum, where is that on the table? You will basically locate it on the table. And the idea is that you have to ask yourself this question. The species on the reactant side, that is by itself, the neutral species, is that higher on the list than the element that is about to be displaced or not? And since the element that is present here is a metal, it could also be hydrogen. So if this is a metal or hydrogen, the species by itself, you will be substituting or displacing the cation of the ionic species. And if the neutral element is anything else other than a metal or hydrogen, basically a non-metal, then you'll be displacing the anion. But right here, since aluminum is the species by itself, we know that this will be displacing the cation since aluminum is a metal. Okay, in addition to that, we need to ask ourselves this question. Is aluminum higher on the list than iron, the species that is displacing? And so you look at the table and you say, well, yeah, aluminum is indeed higher than iron on the activity series. So what this tells you is that the reaction will proceed. This reaction takes place. And so at this point, you carry forward your typical single displacement reaction. Aluminum only has one possibility for its charge. It will be 3 plus. And you'll be now combining aluminum with nitrate. So you got to make sure to place nitrate as a unit with this corresponding charge. Iron, on the other hand, will be by itself. It will be neutral now. And now you use the charges to come up with the proportions. Cross multiply, and you end up with your aluminum nitrate, AQ, plus your iron. So this is how you have done your single displacement reactions in the past. The only extra feature that's being added right now is that we are asking the question, does the reaction actually happen? Yes or no? And in this case, it will happen because the aluminum, the species by itself on the reactant side, is higher than the species that is trying to displace. At this point, don't forget you still need to balance equations, right? So especially if I ask you to do that. So you have 2 nitrates on the left side, you have 3 nitrates on the product side, so you have to cross multiply to balance the nitrates. Multiply the iron nitrate by 3 and the aluminum nitrate by 2 to balance the nitrates. And at this point, you need to balance the irons. You have 3 on the left side, 1 on the right side, so you need to multiply that by 3. And for aluminum, you have 2 on the right side, so you need to multiply the one on the left side by 2 as well. All right, so let's do another example. Here you have mercury, and this is mercury 2. By the way, you don't have the little subscript 2, so this is mercury 2 by default. Mercury 2 chloride reacting with H2. Now, H2 is the element by itself. So that's the one that we want to ask the questions. Is this species higher on the list than the mercury that it's about to displace? And so we look at the list and we see that hydrogen is in fact higher than mercury. So this reaction will take place. And here you carry out your process of predicting your products. Hydrogen will displace mercury, so the moment that happens, hydrogen will develop a charge, specifically H+. Since it's displacing a cation, hydrogen still needs to be a cation. It will be in combination with chloride, so we're going to combine those two together. And the mercury, on the other hand, is going to be by itself. And by itself, mercury is a liquid. Then you use the charges, cross-multiply to bring the species together, so you have HClAq. And at this point, don't forget to balance. You have 2 chlorines on the left side, only 1 on the right side, so you multiply that by 2, which also means that you have 2 hydrogens on the right side, but you have 2 on the left side, so this works out. All right, let's do another example. We have now potassium with water. Now, this is a little bit tricky because nowhere on the list do we have water present. But once again, this is a single displacement reaction because one of the reactants is by itself in elemental form, specifically potassium. So we're asking the question, is potassium higher on the list than the cation of water? And the cation of water is basically H. Now, if you rewrite water the way I have it right here, HOH, then it becomes pretty obvious that potassium has to be displacing the hydrogen here on the left. So we're going to be asking the question, is potassium higher on the list than hydrogen? And if you look at the list, potassium is up here and hydrogen is all the way down here. So this is definitely going to happen. In fact, not only does it happen, but because they are so far apart on the table, this reaction is actually a little bit dangerous if you're not conscientious about how you're performing it. So I personally wouldn't recommend that you do this. This is kind of a dangerous reaction. So what you would do is substitute the first hydrogen with the potassium. So you end up with potassium plus, and what you have left over is OH, specifically OH minus, also known as hydroxide. Now the H that you're displacing by itself is one of the diatomic Hofbrinkel elements, so you have to write it as H2 gas specifically. And then you use the charges to cross multiply and come up with a proportion. And just make sure that everything is balanced. We have 1 potassium, 1 potassium. We have 1 oxygen, 1 oxygen, but then we only have 2 hydrogens, and right here we have 3. So really to balance this, you're going to have to multiply the water by 2 and specifically the potassium hydroxide by 2, so that you end up with the same number of hydrogens. This will give you 4 hydrogens altogether on the right side, and you have 4 hydrogens altogether on the left side. And of course, because we multiply the hydroxide by 2, we have changed the proportion of potassium, so don't forget to add the 2 in front of the original potassium. Alright, so the second thing to be mentioned is that anion exchange can happen in the course of the reactions, right? And this will take place if and only if the lone species, in this case C, happens to be a non-metal other than hydrogen. Okay, so if this species, the lone species, is not a metal and it's not hydrogen, you're going to be exchanging the anion. So let's take a look at some examples of that sort. We have F2 as the lone species. F2 is neither a metal nor hydrogen, so now the displacement will take place with the anion. And so what we do is we compare and say, okay, between fluorine and bromine, fluorine is higher on the list than bromine, so this reaction is going to happen. And between chlorine and bromine, chlorine is higher on the list than bromine, so that reaction will also happen. So what we do is we keep the magnesium or the scandium the same, because that's not getting displaced. That's actually the common thing between the two equations. But the fluoride will now be in combination with magnesium. The bromide was getting displaced, so you're going to end up making Br2 liquid as a byproduct. You use the charges to come with a proportion. Same thing here. Scandium is going to remain the same because what we're displacing is now the anion. So chloride will now be in combination with scandium. Bromine will be kicked out by itself. And now you use the charges to cross multiply on both instances, giving you MgF2 and SeCl3. Alright, so now not only have we determined that these reactions do happen, we have predicted the products, we use the amounts to balance the equations. And looking at the first equation, we have two fluorines on both sides of the equations. We have two bromines on both sides of the equations and one magnesium. The equation is balanced, nothing to be done there. Over here, however, we have two chlorines on the left side, three on the right side. So we have that even odd business. So we need to multiply the two chlorines by 3, excuse me, and the 3 chlorines of scandium chloride by 2. That changes the amount of scandium. Now we have two scandiums on the right side, only one on the left side. So we multiply that by 2, and of course that changes the amount of bromine. We now have 6 bromines on the left side, so we need to multiply the Br2 by 3. And alright, so there you have it. This is the activity series, is an addendum to single displacement reactions from the point of view of oxidations and reductions. So this marks the last lecture of this series. I hope you've enjoyed it. I hope you learned a good amount of material, and that it will serve to help you in the future in your in your next set of classes that involve chemistry. All right, with that being said, thank you for watching. It's been a pleasure, and you have a good rest of the semester. Bye bye.